Okay, good morning and welcome. Today we will give an introduction about the wavelets. Okay, wavelets, or you can say wavelet analysis. So we will see how the wavelet analysis is different from the Fourier analysis and how wavelet transform is used in different applications, especially for signal processing. Okay, so what is the difference between a wave and a wavelet? Okay, when you say we have a wave is basically oscillating function of time or space. Okay, like you have a sine wave or a cosine wave, so it has some oscillations as a function of time. Okay, and generally a wave, it exists from minus to plus infinity, or it is of infinite duration. Okay, so the Fourier analysis that you have studied, it is basically a wave analysis. Okay, because we decompose in the Fourier series or the Fourier transform a function f of t in terms of sine and cosine functions, which are waves. Okay, so we say that the Fourier is a wave analysis. Okay. And as long as this function is stationary, or it is periodic, or it is time invariant, so Fourier analysis is a very well-defined mathematical tool for the analysis of stationary phenomena, okay, or the periodic phenomena. But if the signal has some transient variations, or if the signal is non-stationary, or if the phenomena is time-varying phenomena, so in that case wavelet analysis is more suited. Okay, so what is a wavelet? Basically, a wavelet is a small wave okay, in which maybe I define a small wave like this. Okay, the energy of which is concentrated in time. Okay, it is not of infinite duration extending from minus to plus infinity. Its time duration is finite, or if we say it is a compact support. Okay, as a result, it gives you a tool for the analysis of transient or non-stationary or time-varying phenomena. Okay, so generally this wave, which we call it as a wavelet of finite duration, its average value is 0. Okay, so you can say that wavelet is a small wave with 0 average value. Okay, now before we see what actually wavelet analysis is, let us turn to a basic notation used in signal processing. In the signal processing, we say that if you have a function f of t, this function can be better analyzed, or it can be better described or processed if you can express this function as a linear combination of some other functions. Okay, if this function can be decomposed in the form of a linear superposition or a linear combination of some other functions which I have written as psi kt, and then these coefficients ak, which are some real valued coefficients, these are called as expansion coefficients. Okay, and if this decomposition is unique, in that case the set of these functions, we call them as basis functions. Okay, so if a function of time, it can be decomposed as a linear combination of some other functions, and if that decomposition is unique, we call these functions as the basis functions. Or you can say alternately that a function f of t can be decomposed as a0 maybe psi naught t, psi 0 t plus a1 psi 1 t and so on. Okay, so this set of functions psi 1 t, psi 0 t, psi 2 t, these are basis functions. And these a0, a1, a2, which are real valued coefficients, they are called as expansion coefficients. Okay, and you will see that these expansion coefficients ak, they can be computed from the inner product of this function ft with these basis functions if the basis functions are orthogonal. Okay. If the basis set is orthogonal, in that case these expansion coefficients, they can be computed from the inner product of the function with the basis function. Okay, and you will see that if the basis functions are orthogonal, okay, if the basis function is orthogonal, it means if you take two basis functions psi kt and psi lt, where k is not equal to L, their inner product will be 0 for k not equal to L. Okay, so inner product means that if you multiply them and if you integrate them, this integration turns to be 0. This is what is orthogonal. Okay, so if you take any two basis function from this expansion set, they will be orthogonal to each other. Okay, and if they are orthogonal to each other, in that case this ak, which is the inner product of f of t with psi kt, or you can write it as ft psi kt dt. If the basis function is orthogonal and ft has been expressed in the form of a series as a linear combination of some other basis functions, you can write it as, in place of this, summation of ak psi kt into psi lt dt. Okay, in place of k I used the variable L here. And if these two functions psi k and psi lt, they are orthogonal to each other, in that case this inner product will give you a single value of ak. Okay, this ak from the inner product of the function with the basis function gives you a single value if the basis function are orthogonal to each other. Okay, because it is integration, you can write it as, if you replace summation and integration, so you can write it as summation of ak psi kt into psi lt dt. So this product is 0 if k is not equal to L. Okay, and when k is equal to L, this integration becomes somehow a finite integration. Okay, so that in this summation of k, which may go from minus to plus infinity, you will get only one value of k for which this integration will take a finite value. Okay, so if the basis function is not orthogonal, then there may exist some other dual basis set, so that you can obtain AK using the inner product of this time function with that basis function. So that decomposition in that case may not be unique. Okay, let me explain this using the Fourier series. What we do in the Fourier series is that you have a function which is periodic. If we have a periodic function, so what the Fourier series does, it decomposes this function in the form of complex exponentials only. Okay, now if you compare this decomposition with the general case that we have just described, I have taken that any function, if it can be decomposed in this form, summation of ak psi kt, where ak are the expansion coefficients and psi kt the set of all these functions, it is the basis function. So in case of Fourier series, so the psi kt function is basically replaced with e raised to power j omega naught kt, and you will see that e raised to power j omega naught kt for different values of k, they are orthogonal to each other, or this expansion set is basically a orthogonal expansion set. So if you take two basis functions, one is, so in this case my psi kt, the expansion function or the basis function is e raised to power j omega naught kt. So if you take two functions and integrate them, if you take psi kt and psi lt dt, integration for one time period, so you will get e raised to power j omega naught kt into e raised to power j omega naught lt dt. So this integration will turn to be e raised to power j omega naught k plus l times t into dt. Okay, so it will become cos, integration of cos omega naught k plus l t dt plus j integration of sine omega naught k plus lt dt, isn't it? So it is cos plus sine, integration over one time period for both. So what is the integration of this function? Integration of cos omega naught k plus lt dt for one time period, and integration of sine omega naught k plus lt dt for one time period. So this is a periodic function, and since k and l both are integers, so k plus l will also be an integer value. So let us, I write it as m. So k omega naught m, sine omega naught m here. So if you take cos of omega naught t, this is a periodic function, and the time period of this is 2 pi by omega naught. Okay, similarly for sine and cosine, they are both same, there is only a phase difference of pi by 2. So now my function in case of cos omega t, my function is cos of omega naught mt, where m is an integer. So what is the time period for this? Take it as t1, it will be 2 pi by m omega naught, or in terms of t I can write it as t by m, because 2 pi by omega naught is my t. Okay, so t1 is t by m. So if cos omega naught has a time period t, the time period of cos omega naught m or m omega naught will be t by m. Okay, it means time period, suppose if m is 2, if it is cos 2 omega naught, so time period will be half. If it is 4 omega naught, so time period of this function cos 4 omega naught will be 1/4 of the time period of cos omega t. So if I take cos omega naught t or sin omega naught t, whatever it is, if this is my cos omega naught t, okay, this is one time period t, which is equal to 2 pi by omega naught. And if I now take cos of m omega naught t, this function, it has a time period of t by m. Okay, it means in one time period you will have basically now t by m cycles. Okay, because time period is reduced, so frequency is somehow increased, you can say. Okay, if it is m is 2, your time period will be t by 2, half of this. It means in one cycle of this function we are getting the 2 cycles of this functions. Okay, so one cycle, then 2 cycles, like this. This is t1, which is t by 2. This much is t1, or t is 2 times t1. Okay, what basically I am trying to say that in the integration of cos omega naught mt dt, you are getting basically m cycles of a cosine function. Okay, you are getting the m cycles, and if you integrate it for one time period of cos function, and this one time period is for this function. Okay, and within this one time period you are getting multiple time periods or multiple cycles. Now since the integration of the cosine and sine both for one time period is 0, so the integration of this function for a time period which have multiple cycles for 2 time periods or 3 time periods, it will also be 0. Okay, so both these integrations, they will turn to be 0. So as a result, this entire integration is 0. So these two functions, they are orthogonal to each other. Okay, so this expansion set, it basically becomes a orthogonal set. Now if this is a decomposition, if I can decompose a function like this, it means I can find, and since this is a basis set now, I can find the Fourier series coefficients, which are called as the expansion coefficients, using the inner product of function with the basis function. Okay, and since the basis functions are orthogonal, so the inner product of the function with the basis functions will give you a unique value of, or single value of this coefficient. Okay, this is what is the beauty of this. So you have a function f of t, which we have expressed as a linear combination of complex exponential signals, which we call as harmonics basically, because the frequencies of these are harmonics. So you have one frequency with omega naught, then another with 2 omega naught, then 3 omega naught, and so on. Okay, so to compute this AK, we have to use the inner product of the function with the basis function. Okay, so in order to find this AK, what we do, I multiply this function of t, the basis function e raised to the power minus j omega naught lt on both sides, and then we integrate it for over one time period. And similarly on the right hand side, you will have integration of ak e raised to the power j omega naught kt multiplied with e raised to the power minus j omega naught lt dt. So if you replace this integration and this summation, you will have here integration over one time period e raised to the power j omega naught k minus lt dt. And again this integration will be cos plus sine if k is not equal to L. this integration will turn out to be 0. And if k is equal to L, in that case, so this integration is 0. If k is not equal to L, it means now these functions are orthogonal to each other. And if k is equal to L, when in this series k is equal to L, you will get e raised to power 0, that is 1t integration over one time period, so it will become t. It will become integration of dt 0 to t, so t minus 0 is t. Okay, so this integration on the right side, left side, integration of ft e raised to power minus j omega naught lt dt, it will become al into t. Okay, so in this entire series you will get just only one value, non-zero value, when L becomes equal to k. Okay, and that will be equal to t, so t multiplied with al. So from this you can find al, which is 1 by t integration of f of t e raised to power minus j omega naught lt dt. Okay, or if you change this variable here, L to k, you can write it as ak is equal to 1 by t integration over integration of f of t e raised to power minus j omega naught kt dt. Okay, this is what is inverse Fourier series in the Fourier series relationships. Okay, so given a function f of t which is periodic in nature, you can find the expansion set coefficients, which we call as the Fourier series coefficients, from this equation as the inner product of the function with the basis functions. And once you obtain these coefficients ak, so you can put these coefficients into this equation, and this function will be represented in a different form as a linear combination of complex exponential. Okay, so this Fourier series is basically a mapping where the function f of t is mapped to a sequence of coefficients ak. So you have a0 means when k is 0, your omega naught is 0. So this gives you the DC component. Okay, then a1, which corresponds to omega naught frequency, so it gives the amplitude of this frequency omega naught. Then you have a2, what is the amplitude of a2? Okay, so if you add all these complex exponentials together, you will get this series f of t. So this is the alternate way to decompose a function in terms of in a different format. Okay, and whenever we decompose a function f of t, one dimensional, it may be two dimensional when you set to images. So if you decompose a function in this form, a general decomposition, so there are two reasons behind that. One is that the information in this domain, in the transform domain, you can say the coefficients ak, they give some more insight or give some information which is directly not available from the signal itself. Okay, and another important feature that we use in the wavelets is that these coefficients, for most of the values of k or these expansion coefficients, they are 0. Okay, which is called as sparse representation. It means the signal can be represented by few coefficients in this domain only. Okay, see, like in the Fourier series, if you decompose a sequence, if you decompose a function in the form of a series ak e raised to power j omega naught kt, what is the advantage of this? Why we decompose a Fourier series like this, or a function like this, if the function is periodic? This gives you the frequency domain representation, that what are the various frequencies present in the signal. Because now here we have this function after Fourier series is mapped to a sequence of coefficients. So you have a0, then you have a coefficient a1, a2, a3, and so on. So in terms of frequency, this frequency is your omega naught, this is 2 omega naught, and so on. Okay. So this decomposition says that what are the various frequencies present in the signal and what is their corresponding amplitudes. So if you combine all these frequencies together, you can reconstruct the signal using the complex exponentials only, or in terms of sine and cosine functions only. Okay. So one advantage is this, that any periodic signal, it can be generated from complex exponentials only. Okay. Or it can be generated from sine and cosine functions only. Another important property or the feature of the Fourier series is that when you decompose a function like this in the form of a series like this, a0 plus a1 e raised to power j omega naught t plus a2 e raised to power 2 omega naught t and so on. So we have decomposed the signal as a linear combination of different signals. So this is one signal a naught constant, then constant multiplied with exponential and so on. Now when you study the problem of filtering, what we say, when you pass this function through a linear time invariant system, how you find the output. Okay, in time domain, it is the convolution between the input and the impulse response of the system. Otherwise, now I say alternately, if I decompose this function as a linear combination of complex exponential, that is, I have denoted now of t as a1 e raised to power j omega naught t plus so on, and since the system is linear, the output of this system will be the sum of their individual outputs. So when you have a naught as the input, your output is a naught. Okay, when you have a1 e raised to power j omega naught t as the output, so there is a property of the linear time invariant systems that if you apply purely complex exponential to a system, the output of this is the same complex exponential multiplied with the frequency response of the system at that particular frequency. Okay, so it has some impulse response ht. If you take its Fourier transform, that is called as h of omega. Okay, so frequency response. So each frequency is basically multiplied with its corresponding frequency response. So if you decompose a function in the form of a series like this, so their individual outputs can be combined together. So you will get here a1 h omega 1 into e raised to power j omega naught t omega naught. Next will be your a2 h of 2 omega naught into e raised to power j 2 omega naught t. Okay, so this gives you a concept for filtering. Okay, now since the input signal is decomposed in terms of the various frequencies which are present in the signal, so the corresponding system through which you are passing the signal, these frequencies will be multiplied with the frequency response of the system at those frequencies. So if you had some particular frequency response is 0, so that frequency is simply stopped by the filter. Suppose h omega naught is 0, so this frequency is stopped by the system. It will not appear at the output. This is how filters are designed. Okay, so whenever we decompose a function as a linear combination of some other basis functions, it means that representation or these expansion coefficients, they provide you some information which will not directly be available from the signal itself. Okay, or in simple terms, you can say that if you take a simple square wave and I ask you that what are the various frequencies present in the signal. So by looking to this signal in time domain, it is a function of time. You are not able to tell what are the frequencies present. Okay, but if you apply Fourier series on this, okay, you can see that what are the various frequencies that will be present in the signal. Okay, so we will have one frequency omega naught, then we will have 2 omega naught, then we will have 3 omega naught. Okay, and a0, a1, a1, a2, a3, these will be their expansion coefficients which give the corresponding amplitude of those frequencies. So if you combine those frequencies together, you can get this square wave. Okay, this is how any periodic signal is built from the complex exponentials. Now how this wavelet analysis is different from this Fourier series. It is very much similar to the Fourier series, that we again decompose a function of time, one-dimensional function. In the Fourier series, we decompose the function in terms of complex exponentials which form a orthogonal basis. And in the wavelet analysis, we decompose this function in terms of wavelets. Okay, the basis functions in case of Fourier transform analysis, they are fixed, sine and cosine. Okay, so every signal has to be decomposed in terms of sine and cosine only. But if the signal is somehow non-stationary or time varying, or there is some transient phenomena in the signal, so that cannot be actually represented well in the Fourier series. See, if you say simply take a square wave, so it has some discontinuity at this point, these points. Okay, so if you say that you decompose the signal in terms of the Fourier series, so you have to have different sine and cosine functions with different amplitudes, you will get this wave. Okay, so if you take one wave only, one cosine function, you may get this. If you add two functions or more functions, you will get a wave like this. If we add more and more functions, this will become more smooth. It will turn towards a square wave. So even if you add infinite number of components, what you will get basically is that. Okay, so where the signal is constant, you can get a constant part in its Fourier series representation, but where there is a discontinuity, there will be always some ripples, which is called as Gibbs phenomena. Okay, so the discontinuities in these functions, they basically are not well represented in the Fourier series. The reason is that since we are using only the sine and cosine functions, we have only two functions. Either you can use a cos wave or use a sine wave. Okay, and since these functions, they themselves are very smooth functions, so how you can add them to create a discontinuous point. Okay, so that can be done only if you introduce some phase differences, because the phases will cancel each other and somehow you can create a discontinuity. Okay, that is the only solution. So that is why there are transient signals, they are basically not well decomposed or represented in the form of Fourier series, because the Fourier basis functions, they are smooth functions, the sine and cosine functions. Okay, and the basis functions are fixed. Okay, so once we choose or once we select that, okay, I use Fourier analysis for this signal, it means your basis functions are fixed, you have sine and cosine functions only at hand. But in the wavelet analysis, this is not the case. The basis functions, they are not fixed. You have a family of wavelets basically. So for any particular signal, you can choose any one of those wavelets to decompose this function in terms of wavelets. Okay, so again, you have a function f of t. Now we decompose this function in terms of wavelets, not in terms of complex exponentials. And wavelet expansion is a two-parameter expansion. You have two-dimensional coefficients a, j, k, psi, j, k, t. This is what is in generally wavelet expansion. Okay, so you have a one-dimensional function of time which may be periodic, not periodic. Okay, in the Fourier series, this function has to be periodic. Okay, in the wavelet analysis, this restriction is not there. Any function f of t, it can be decomposed like this, where psi, j, k, t, these are called as wavelets. So wavelets are basically not continuous waves of infinite durations. They are small waves of finite duration in time. So they have compact spot in time. Okay, or we can say they are localized in time as well as in frequency. So as a result, it gives you a time frequency analysis tool. You can analyze simultaneously a signal in time as well as in the frequency. Okay, in the Fourier series, it is only frequency analysis. You convert a signal from time to frequency. So you have only frequency resolution, no time resolution. But in the wavelets analysis, we will see that it provides a simultaneous time frequency analysis of the signal. Okay. Now these coefficients, now this is a two-dimensional array of coefficients. It means in the Fourier series, what we have done, we have mapped a function of t to a series of coefficients ak, which we call as the Fourier series coefficient. In case of wavelets, this is for Fourier series. In case of wavelets, this function is mapped to a two-dimensional array of coefficients ajk. Okay, so j, where j and k, they belongs to integers. Okay, so you can have j is equal to 1, k is equal to 1, you will get one coefficient. J is equal to 1, k is equal to 2, another coefficient. J is equal to 1, k is equal to 3, another coefficient, and so on. Okay, so that is why we have double summation here, summation over k and summation over j. And psi of jkt, these functions are basically obtained from a single function which is called as the mother wavelet, where j corresponds to an operation which is called as scaling and k corresponds to an operation which is called as translation. Okay, so a single function psi k, psi of t, psi of t is a single function which is called as the mother wavelet, and this psi jkt with indices of j and k, this is obtained from psi t only. So we have a mechanism to generate psi jkt from t, which is 2 raised to power j psi of 2 raised to power j t minus k. Okay, this is how psi jkt is generated from psi t. So psi t is a basic wavelet which we generally call as a mother wavelet, and all these functions, they are generated from the same wavelet using the scaling and translation. So j is scaling, k is translation or shifting. So if you see this k index, it is psi of 2 to the power jt minus k. So minus k means it is shifted in time, translation, or we call it as shifting. And j is scaling, so you're multiplying t with 2 raised to the power j. So somehow this signal is either compressed or it is expanded in time. Okay, so it means if you have a signal, if you want to decompose the signal in terms of the wavelets, so what we do, we choose a wavelet function, a mother wavelet, and then we shift this wavelet along the time axis. Okay, and correspondingly for each shift and for each scale, we compute some real valued coefficients which we call as the wavelet transform or discrete wavelet transform of the signal. This is called as DWT. Okay, and then we change the scale j. Let me first explain what is this scaling property. So you have a single wavelet psi t is a wavelet function which is mother wavelet, and psi jkt, how we have generated this from this function, is 2 raised to power j psi 2 raised to power j t minus k. Okay, so this function is basically multiplied with 2 raised to power j so that the energy of the functions remains same at each scale. Okay, this is just normalized energy. Or you can see, if you find the energy of this function psi jkt scale, this is energy of this function. Okay, and you will see that it is same as the energy of this function because of this scaling factor. If you take this modulus of this and square it and integrate, if you take the square of this 2 raised to power it is j by 2 here, sorry, j by 2, which will maintain this constant energy in the signal. So this, if you square it, 2 to the power j by 2 square, okay, into psi of 2 to the power j into t minus k square dt, you will get it as 2 to the power j here, and then psi square 2 to the power j t minus k dt. So if you replace this, if you put 2 to the power j t minus k is equal to suppose x, so this will become integration of 2 to the power j into psi square x into dt. So dt, from this you will get dx by 2 to the power j. So this 2 to the power j and 2 to the power j gets cancelled. You will get again psi square x into dx. So this is the same as the energy of this function psi t. Okay. So this 2 to the power j by 2 scaling factor is used to normalize the energy. Now what is this 2 to the power j and k here? Suppose I put j is equal to 1 and k is equal to 1. It means I get one function psi of 1 t. Okay, so leave this scaling factor, just concentrate on this. It will be 2 to the power t minus 1, isn't it? So scale is 1, translation is 1. Okay, so psi 2t minus 1, how this function is obtained from psi t? It is shifted and it is scaled. So by what amount it is scaled and by what amount is shifted? So if you have psi of t as the original function, mother wavelet, if you scale it by 2, you will get psi 2t first. So scale by 2 means it is basically compressed by a factor of 2. Okay, its time limit, it becomes half. So if I take this function, let us suppose this is one function. If this is a function 0 to 1, it is 1. If this is suppose psi t, what will be psi 2t? It will be compressed by a factor of half. It will go from 0 to 1 by 2 only. This is psi of 2t. And after the scaling, I have to shift it so that I get 2t minus 1. So if I shift it by 1 to the right, I will get twice of t minus 1. It will become psi of 2t minus 2 basically, but I have to get here 1, so I have to shift it by half. Okay, so that I will get psi of 2t minus 1. So after this scaling, if I shift it by 1 by 2 to the right, so this function will become like this. So 0 will come to 1 by 2, 1 by 2 will go to 1. So this function is psi of 2t minus 1. Okay. So using j, which is a scale, we are basically compressing the signal. So if j is 1, it is compressed by a factor of 2. If j is 2, it is 2 to the power 2, 4. It is compressed by a factor of 4. Now if it is compressed by a factor of 4, and k if you take still 1, it will be now 4t minus 1 by 4 here. Okay, then only will get 4t minus 1. Otherwise, in general, you can say that if you scale this function psi t by a factor of 2 to the power j, it has to be shifted in time by k by 2 to the power j, so that you get psi of 2 to the power jt minus k, isn't it? So psi t if you scale it by, if you first scale it, it becomes psi 2 to the power j t. Why use 2 to the power j t? There is an important reason for that we will discuss later. It is basically it gives a logarithmic scale. Okay, so we scale by 2, then 2 to the power 2 4, 2 to the power 3 8, 16, 32, and so on. Okay, depending upon j, and then depending upon k, when you shift it by some index k, whatever the k may be, it means you have to shift it by 2 raised to the power j. If you want to get t minus k, it should be t minus k upon 2 to the power j. So if you compress it by 2 to the power j factor, you have to shift the signal in time by k divided by 2 to the power j, so that you get psi of 2 to the power jt minus k. Okay. So in general, you can see if it is 2t minus 1, it means you are compressing it by a factor of 2 and then you are shifting it by 1 by 2. So you compress the function wavelet in time to half and then you shift by half time. Okay. If you compress it by 4t, compress by a factor of 4, then you have to shift by 1 by 4. Okay. So it is this property of translation and this your scaling which allows the time localization of the events in the signal. Okay, so what do you choose in this wavelets? So you have a function of t. If you want to represent this function in terms of the wavelets, so you have a two-dimensional or two-parameter set, a jk psi of jkt, where these expansion coefficients, they can be again computed using the inner product of the function with the basis function if the basis function is orthogonal. Okay, and these coefficients we call them as discrete wavelet transform of this function of t. Okay, so again, if you decompose a function like this, it means this decomposition will give you some more information which cannot be available directly from the signal itself. Okay, and there are two things behind this. That one is that these coefficients, they give you time frequency localization of the signal for different values of j and k. Okay, because when you change j, you are changing the scale, or you are compressing the signal or stretching the signal. Okay, so you basically have a time scale. This is j, this is k. So on this axis, if you go on increasing the j, suppose j is 1, then 2, then 3, then 4. So when j is 1 and then k is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. So j is 1, k is 1, you will get one coefficient here, suppose, or when j is, okay, so a of 1, 1, then another coefficient will be a of 1, 2, j is 1, k is 2, then a of 1, 3, and so on. These are like these dots, these basically denote these coefficients which have some values. And when we go to j is equal to 2, next scale, you are compressing the wavelet by half, and if k is 1, it means you are shifting by half now. Okay, so you will have one coefficient here, then one coefficient here, then one coefficient here, then one coefficient here, because the wavelet is compressed in time by half, and now the shifting has to be done in half intervals. Okay, then if it is 3, it is compressed by a factor of 8. Okay, and so on, like this. For 2 it is 4, in fact. For j is equal to 1, in fact it is by 2. Okay, if k is j is 0, in that case it is the original, you can say wavelet. ये 2 यहाँ पे आना था 2, because j is equal to 1 scale means 2 to the power j, it is compressed by a factor of 2. So shifting will be done in 1 by 2, 1 by 2, 1 by 2, and so on. Okay, and so on. So as you change the scale, you are basically compressing the wavelets and you are shifting the wavelets in time in small durations. Okay, this is how the wavelet transform. It captures the various transient phenomena in the signal. So if you have some signal like this, maybe a pulse, simple pulse, you want to decompose this pulse in terms of wavelets. So what you have to do, you have to first choose a mother wavelet. Let us suppose you choose a wavelet like this, a small wave which has finite duration. Now this function has to be decomposed or expressed in terms of this function only. Okay, it means you have to find these coefficients for different scales and different translates. So you may start from here and end up to here. So you may have one function here. Okay, then we have another function here. So you multiply this with some, you may decrease the amplitude of this by multiplying with some coefficients. Okay, if you multiply with -1, it may get, its phase may get reversed. Okay, then you compress it by some scale and then you shift it by half of the intervals and so on. Okay, so you will get one set of coefficients here, a0 of k, then a1 of k, and so on. Okay, so a0 means scale is now fixed to 0, so you can put k is equal to 1, shift by 1, k is equal to 2, k is equal to 3. Okay, so if it is first coefficient a0 1, it means what at that time and that scale I have wavelet, I have to multiply it with that constant and shift it, multiply with another constant, then I compress it, again shift it, multiply with another coefficient. So if you add all these functions together, you can get this wave. This is what is the wavelet transform. Okay, so function is finally decomposed in terms of the wavelets, and all the wavelets, they are in fact generated from a single wavelet by using translation and dilation. So translation is basically time shifting operation where we shift the wavelet along the time axis, and your scaling operation is basically either stretching or compressing the wavelet in time. So the more you increase the scale, it means the higher resolution you will get or the more details you will get, because this function will be compressed in time. So if you want to suppose tackle this discontinuity in the function, so for this discontinuity the function should be very small or narrow in time. So it may have a function like this, a wavelet function. So this information will be captured by a narrow wavelet. Okay, so the detailed informations, they are basically captured by at high scales, and the coarse informations which we call as, they are captured at low scales. Okay, and this translation parameter k defines you that okay, at which point in time that discontinuity or that information is located. Okay, because when you change the scale, you are compressing the wavelet or stretching the wavelet. It means somehow you are changing the frequency, because when you choose a mother wavelet psi of t, it has its own frequency response, it has some frequency. So if you change the scale of this, its frequency will be changed. Okay, so yeah, it may become double, it may become half. And then when you shift the wavelet along the time axis, at which time and at which frequency, those coefficients which give you the high values, it means that particular frequency is basically present at that particular instant of time. So this is how they provide time and the frequency information simultaneously. Okay, so what are the way what is the main advantage of the wavelets or the Fourier analysis is that, so when we decompose a function in terms of the wavelets, later on we will see that we use one more function which is called as a scaling function along with wavelets. In fact, the wavelets, they are basically operand from the scaling functions, but forget that for this time. So a function of f(t) is decomposed in the form of a series, a two-parameter system like this, and these coefficients, they becomes my discrete wavelet transform. Okay, and this becomes basically inverse wavelet transform. Okay, which gives a equation to reconstruct this function f(t) from this expansion coefficients ajk. Okay, now again there are two main reasons why we decompose a function like this. One thing is that you may get some more information from these coefficients which will not be directly obtained from this function itself. Okay, and the second thing is that most of the coefficients in the expansion of this function ajk, they are zeros. Okay, which is basically called as a sparse representation of the signal, and which is very useful when you use these wavelets for data compression or image compression. Okay, so a signal, or we have one-dimensional signal, or you may have a two-dimensional signal, image. Okay, so when you apply the wavelet transform on this, so we decompose the signal now in terms of the basis functions, which are wavelets itself. Okay, and since wavelets, we have a family of wavelets, so we are not restricted just to sine and cosine functions like in case of Fourier analysis. Okay, so you can choose from a wide range of wavelets, any particular wavelets which is best suited for your signal. Okay, and then we decompose this function, one-dimensional or two-dimensional function, in terms of the wavelets functions. So we get some coefficients ajk, which gives the time and the frequency information about that signal simultaneously. Okay, so for most of the signals, when you decompose the signal in terms of the basis functions wavelets, these coefficients ajk, they are almost zero. It means the signal information, the information about the signal or the energy of the signal, that can be stored only using the phi coefficients. This is how the data is compressed using the wavelets. Okay, and similarly when you use wavelets for this denoising, if a signal is corrupted by noise and you have to remove the noise part from the signal, so when you apply the wavelet transform on this, so there are some coefficients in this wavelet domain which contain the noisy components of the signal or the image. Okay, so some coefficients of the DWT, they will capture the noisy component, and if you just make those components equal to 0 and you apply this inverse transform, you can get a noise free signal. Okay, this is how wavelets they are used. So wavelets, they have so many applications in signal processing, in communication, in biomedical analysis. Okay, so mostly they are used for denoising and compression. Okay, and how they are used for denoising and compression, that I have just given you overview. That you apply wavelet transform, and if most of the coefficients are zeros, you can simply discard them. You can store this information only using phi wavelet DWT coefficients. Your data will be compressed. Okay, and if you want to denoise a signal, so you apply some wavelet transform on a signal, and the noisy components, the noise in the signal will be captured by phi coefficients in the wavelet domain. And if you delete those coefficients and you apply inverse transform, your signal can be noise free. Okay, so we will further continue on this. Thank you.